we know that chapter 6 continuous probability distribution, when we compare the chapter number 5, chapter 6, I would say that the importance if the chapter 6 is the 10 points and the chapter 5 we will just have 5 or 6 points, that's not very high. So this one is very important because this one will affect the following learning. So I encourage you to learn this one. Okay. In chapter 5, dealt with probability distribution arising from discrete random variable. Most of the chapter focused on binomial experiments, and there are many other experiments for discrete random variables that exist but are not covered in this book. This chapter deals with probability distribution that arise from continuous, compared to the chapter 5, that's discrete. Chapter number 6, that is continuous, random variables. The focus of this chapter is a distribution known as the normal distribution. Normal distribution, that is the most important key concept, the most important concept, critical concept in this chapter, in this subject. Though realize that there are many other distributions that exist, a few others are examined in future chapters. Okay, let's check the chapter number 6.1, uniform distribution. Section 2, graphs of the normal distribution. 6.3, finding probability for the normal distribution. 6.4, assessing normality. And 6.5, sampling distribution and the central limit theorem. Okay, let's check the chapter 6.1, uniform distribution. If you have a situation where the probability is always the same, when this is known as uniform distribution, an example will be weighted for a commuter train. The commuter trains on the blue and green lines in Regional Transit Authority (RTA) in Cleveland, Ohio, have a waiting time during peak hours of 10 minutes. The information source is here. If you are waiting for a train, you are always from 0 minutes to 10 minutes to wait. Your probability of having to wait any number of minutes in that interval is the same. This is uniform distribution. The graph of this distribution is shown as 6.1.1, like this one. Probability waiting times 1 minute, 2 minutes, 3 minutes, 4, 5, 6 to 10 minutes. The probability is the same, 0.1. Yep. Sorry, I forgot it. Sorry. I enjoy my teaching. I forgot your screen. I apologize. Okay, and suppose you want to know the probability that you will have wait between 5 to 10 minutes for the next train. You can look at the probability graphically, such as figure 6.1.2, the red part, the red area of this one. Probability is always 0.1. How would you find this probability? Calculus says that the probability is the area under the curve. Yeah, in the future, I have no idea whether you already taking the course of calculus. I have no idea, but in the future, if you want to study further, and the area of rectangle is length times width. Length, for example, here the area of this, that is 5. The height or the width, that is 0.1, 0.1. Thus, the length is 10 minus 5, that is 5. And the width is 0.1. The probability get a waiting time between 5 to 10 minutes. The probability is 0.5, 0.5. Where the X is the waiting time during peak hours. Okay, let's check the example. Example 6.1.1, finding probabilities in a uniform distribution. The commuter train on the blue and green lines from the Regional Transit Authority in Cleveland, Ohio State, have a waiting time during the peak rush hour period of 10 minutes, like this one. Okay. Question A, state the random variables. X is the random variables equals waiting time during peak hours. Okay. Question B, find the probability that you have to wait between 4 and 6 minutes for a train. You need to wait for 4 to 6, and the probability is here. X is the waiting time, is larger than number 4 minutes, is smaller than 6 minutes, and we can find the area. The rectangle area is the width multiply the length or the height. 6 minus 4, that is 2. 2 times 0.1, that is 0.2. Okay, the probability is 0.2. Question C. Find the probability that you have to wait between 3 and 7 minutes for a train. Thus, probability X is greater than 3, smaller than 7. And this area, we can calculate 7 minus 3, that is 4. 4 times 0.1, that is 0.4. That's it. Okay. Question number D. Find the probability that you have to wait between 0 and 10 minutes for a train. The probability, it's impossible to wait for 11 minutes, it's impossible. But it's very possible to wait for 1 minute, 2 minutes, 3 minutes, even 9 minutes. The probability is the same. Okay. And probability from 0 to 10 minutes. X is greater than 0, smaller than 10. We can calculate that 10 minus 0 times 0.1, that is 1.0. Okay, the question E, find the probability of waiting exact 5 minutes. Okay. Since this will be just one line and the width of the line is 0, then the probability X equals 5. The probability calculation is 0 times 0.1, that's 0. It's impossible. It's exact 5 minutes because the area very, very small. Okay. Okay, let's finish the 6.1 here. Let's move to the next section. Okay, I have to slow down here because we are entering the topic of normal distribution. That is super important. Not very important. It's super important. Okay. Many real-life problems produce a histogram that is a symmetric, unimodular, and bell-shaped continuous probability distribution. Okay. For example, height in a group or in a population, blood pressure, and cholesterol level. However, not every bell-shaped curve is a normal curve. In a normal curve, there is a specific relationship between height and its width. Oh, okay. Normal distribution has a specific relationship between the height from the y-axis and the width x-axis. Okay, let me slow down here. Every normal curve has common features. Those are detailed in figure 6.2.2, 6.2.2, and we can call that the highest point. We call it mu, or we call it average. And move to the right. X move to the right. Here is sigma. And to the left. Here is a sigma. And here, inflection or transition point. What does it mean, transition point? When we have not discussed about the calculus here. Okay, and here, never actually touched to the horizontal axis. Okay, again, theoretically, it's very approaching to the x-axis, very close to the 0, but never actually touches the horizontal axis. Okay, and here, mu plus a sigma, mu in the center is a bell-shaped curve, and mu minus sigma. And the center of the highest point is the population mean. Again, the center of the curve, the highest point is the mean. The transition point, inflection points are places where the curve changes from a hill to a valley. For example, valley here, and here is a hill. It's a transition point from hill to a valley. The distance from the transition point, inference point, are the places where the curve changes from a hill to a valley. Can you imagine that? Let me draw it. Oh, sorry. Okay. Maybe this one is not important. Maybe I can skip it. Okay. And here, the equation that creates this curve, that is a function, the f of x, that equals 1 over sigma times the square root of 2 pi and to the power of e. The whole group to the power of minus 1/2 times x minus q divided by sigma and take the square value of it. When I was a PhD student in the US, one day I tried to plot this one, but x or y equals 10 to the power of x. It's very easy, but I failed. I cannot draw the function of this. I don't know why. Why the German mathematician created this formula? I don't know why. Okay, and here, just in a discrete probability distribution, the object is to find probability of an event occur. However, unlike a discrete probability distribution, where the event can be a single value, in a continuous probability distribution, that even the event must be a range. Okay, I don't know what happened to the computer because it's a warning message. Okay. Don't care about it. Okay. Then calculus tells us to find this, you find the area under the curve above the interval, in the interval from A to B, And can you read this? Can you read this? Previously, we considered about the discrete, the Lambert of the curve. And previous 6.1, we discussed about the uniform distribution. And this one is continuous in the normal distribution. And now the shaped area is the probability that X is between A and B. And here the shaded area is on the right side of the A value, and on the left side of the B here. Okay, how to calculate the probability? I will tell you how to check the tables, and that's one way. And after this, I will give you some useful websites. You just type your information, then click enter. You will get everything you want. You will get everything you want. Okay. Before looking at the process for finding the probability under the normal curve, it is somewhat useful to look at the empirical rule that gives approximate value of this area. The experimental rule, empirical rule, is just an approximation, and it will only be used on this section to give you an idea of what the size of the probability is for different shading. I will tell you how to do that. Sure, when I discuss this one, it's not easy to understand, but when we check the examples, you will do that very quickly. A more precise method for finding probability for the normal curve will be demonstrated in next section. Please do not use the empirical rule except for real rough estimate. Okay, here. The empirical rule for any normal distribution. First one, approximately 68% of the data within one standard deviation of that mean. Okay, let me show you here. Check my mouse cursor here. Close to 68%. And here, 95%. 95%, that is mu plus minus 2 sigma. Plus is here. Minus is here. And I encourage you to memorize those numbers. Again, 68%, 95%, and 99.7%. Okay, let's move. Okay, a minute, please. Okay, chapter 6.3, finding probability of normal distribution. Okay, and this one is a little bit more important than previous one. Okay, the empirical rule is just an approximation that only works for certain rules. Let's check this. And we know to convert a normal distributed x value to a z-score, you need to follow the following formula. Z equals x minus mean divided by sigma. Okay, it's important, right? But you don't need to memorize it, because in my exam, I will allow you to use any kind of tools. Okay. the z-score, the concept is not easy to understand, but you need to learn it. Where mu, or the mean, is the mean of population of x value, and sigma is the standard deviation for a population of the x value. Okay. The z-score is normally distributed with a mean of 0 and a standard deviation of 1. It is known as the standard deviation normal curve. Okay. Once you have the z-score, you can look up the z-score in the standard deviation standard normal distribution table. Okay. Definition 6.3.2 standard normal distribution. The standard normal distribution Z has a mean of mu equals 0. That is the definition. That's the definition. And a standard deviation of sigma equals 1. Mu is 0 and sigma is 1. Okay. Thus, we can see on the x-axis, the bear shape on the top, that's corresponding to the 0. Plus 1 sigma, that is 1. Minus 1 sigma, that's minus 1. It's symmetric. It's symmetric. Okay. Luckily, these days the technology can find probability for you without converting the z-score and looking the probability up in a table. There are many programs available that will calculate the probability for a normal curve, including Excel and TI-8384. Okay, and I prefer to share you with some useful software online application. They are for free to use. Okay. That's normal CDF, and you can type in a lower limit, upper limit, standard deviation. Okay, and let's check the example here. Example 6.3.1, general normal distribution. The length of a human pregnancy is normal distributed with a mean of 272 days with a standard deviation of 9 days. What does it mean? State the random variable here. X equals the length of a human pregnancy. Okay, then find the probability of a pregnancy lasting more than 280 days. Probability to more than 280 days here. And here is the curve. Here's the curve. And again, in the beginning, I will tell you how to check it manually. But maybe next week or later, I will give you some useful website. Then you can type your information through the website and just one click to get all information you need. Okay. Again, the average is 272. 272 is here. 272 is, there is a line here. And the first question, state the random variable. The second question, find the probability of a pregnancy lasting more than 280. More than 280, we can think about that. The grid of the 280 is here. On the right side of this area, shaded area, it means the pregnancy is longer, equal to or longer than 280, and a little bit far away from the 272, the standard. Okay, and how to do that? First, the probability X greater than 280. The area is here. Now draw a picture. Remember, the center of this normal curve is 272. To find the probability on this software, look at the picture. You realize the lower limit is 280. The upper limit is infinity. The calculator does not have infinity on it. So you need to put a real big number. So people like to put in 1000. But before you are working with the numbers that are greater than 1000, then you will have to remember the change of the upper limit. The safest number to use is 1 times 10 to the 99 power of 99, which you put the calculator as 1e99, where the e is the e button on the calculator. The command line like this one. Okay. To find the probability on R, this time I will not teach you about the R. It's a little bit complicated. Instead, I prefer you to use the Google Office and some use for online applications. That is enough for our course. Okay. To find the probability on R always give the probability into the left to the value. The total area under the curve is 1. The concept is the total area under the curve is 1. So if you want the area to the right, then you find the area to the left and subtract from 1. The command look like this one. Now draw a picture. Remember, the center of this normal curve is 272. Not this week, but maybe next week I will show you some great software. You can put the information inside, then click, everything we will get, everything. $272, close to this position. And find the probability on the TI-8384. Looking at the picture, though it is hard to see in this case, the lower limit is negative infinity. Again, the calculator does not have this on it. Put in a really small number, such as -1 times 8 to the power of 99. And the expression is -1 e and 99 . Okay, then calculate the x smaller than 250. But okay, we ignore this one because we don't use the program R. Okay. Thus, the 0.3% of all pregnancy less than 250 days. This is unusual since the probability is less than 5%. And next question, find the translate of the statement into mathematical statement. And now draw a picture. Remember, the center of this normal curve is 272, like this one. Okay. And in this case, the lower limit is 265 and the upper limit is 280. Use the calculator. Okay. Okay, let's check the example 6.3.2. General normal distribution. The mean mathematics SAT score in 2012 was 514, with a standard deviation 117. Total group profile. Okay, the reference is here. Assume the mathematics SAT score is normal distributed. First question, question A. State the random variable. The random variable is mathematics. Second question, find the probability that a person has a mathematics SAT score over 700. 700, okay. Find the probability that a person has a mathematics SAT score of less than 7. Less than 7, okay. Then question E, find the probability that a person has a mathematics SAT score between a 5 and a 650. E, find the mathematics SAT score that represents the top 1% of all score. Okay, let's check it. The solution to the question A. X equals mathematics SAT score. B, first translate the state into a mathematical statement, like this one. And okay, here's the question. What's the probability X greater than 700? 700. Thus, we can put them together. 700, 1 to the power of 99, 514, 117. Okay, please give me 2 more minutes. I will finish this one. Only R is this one. We don't use R this moment. Okay. Okay. Well, I think I can stop here. Then we have a break. Okay. See you later, guys.